Pan from UT Austin. I'll present our work about automatic repair of regular expressions. This is joint work with Qinheping Hu, Gaowei Xu, and Loris D'Antoni. So regular expression is a powerful tool for extracting and transforming data with applications including deep packet inspection, intrusion detection systems, and matching on data streams, and so on. While it is powerful, sometimes it's tedious and error-prone to write them manually. In this case, a user provides a description that a valid Mastercard number should match a number starting between 51 and 55 and followed by 14 other numbers. And also, a set of matches and non-matches are given. However, the given regex is not correct because the first character class is actually equivalent to 1, 2, 3, 4, 5 plus a bar, instead of the union of 5 substrings, 5.1, 5.2, and so on. And in another case, a student tried to submit a regex to match the description that the regex is in alphabet A and B and ending with AB. And the submission is not correct, so a set of strings that could distinguish the submission and the solution is given. And this is the correct answer. So if one can automatically fix this, it could be useful to provide feedbacks. So can the process of repairing expressions be automated? The similarities between these two cases is the incorrect expressions have similar structures as the correct one, and a set of matches and non-matches are given. So here is a repair problem. Given an input expression and a set of examples, which is in ASCII2 and the UTF alphabet, the output should be a modification of R such that it is correct on these examples. Well, in general, the repair problem might have multiple solutions. In this example, the correct regex should match AB repeats twice or more, which is the first solution on the right-hand side, where the second solution just memorizes each positive examples it has seen. As we will see, these two solutions actually have different distance to the input. So if we impose a minimal distance repair constraint, we can rule out the second solution. Here is our notion of distance. It is defined as the summation of number of nodes in the replaced and the replacing subregex in the AST representation. In this example, only the quantifier node 0 to infinity, which is effectively a star, is changed. So the distance is 1 plus 1 equals 2. While in another case, the only way of editing AB star into the right-hand side is to exchange the whole tree. So the distance is 5 plus 11, which is 16. So we could refine our formalization of repair problem by putting a constraint on the fixed expression R prime. It should be not only be correct on examples, but also be the closest one to the input R. The rest of the talk is composed of 3 parts. The first part is how we're gonna enumerate such templates and how we're going to complete such templates using SMT solver and how to generalize solutions. And then we turn into the evaluation section. So a naive approach to this repair problem is to enumerate every concrete regex in an order of increasing distance. So if we're changing the first character class of the input expression, there might be 2 to the 11 expressions at distance 1 because there are 10-digit numbers and a bar summing up to 11 different characters in these examples. And soon we are going to find this will not be scale. So we will remedy this by using template. A template is an expression with holes that could be completed with a character class or an integer. So the first template here is actually equivalent to all the concrete regexes we see in the last page, in the sense that if one can find a solution within these concrete regexes, we can get the same solution by solving this template. And similarly, a template could also have quantifier hole, which could encode the number of repetitions. So how are we going to generate such templates? So assume we are given a template at distance 1 with a single hole. We can either expand the hole into a concatenation of 2 holes, a union of 2 holes, and so on. And we can also add in a new hole by replacing the concrete quantifier node into a quantifier hole. And we can also reduce a sub-regex into a single hole. So given the template, we showcase how our algorithm works by running an example. First, by taking the initial template, by taking the initial expression, we generate a set of initial templates, and we enumerate each template one by one. And for each template T, we ask, is there a completion of T such that it is correct on examples? If not, we invoke the template generation process and adding more templates. And eventually, we will reach a template that could lead to a solution, and the solution is the minimal distance repair to the input. So, although a template is powerful, sometimes it's still too many templates to start with. So we will use some powerful pruning techniques. We will first introduce the sigma test. It tests whether there is a completion of T such that it could accept all positive examples. Observe that if we replace the hole with a dot, which could accept any single character, the resulting regex is the most permissive completion among this template. But still, the positive example is not accepted. So we conclude that the sigma test failed. So we could reject this template immediately without exploring it. The second test is the top test. It tests whether there is any expansion of T whose completion could accept all positives. And since if we expand a hole in any way and trying to complete the holes in the expansion, it will be no more permissive than a dot star. So if we replace a hole with a dot star, the resulting regex is the most permissive completion among all expansion of T. And still, the same positive example is not accepted. So we could reject all the expansions from T. And finally, we will introduce bottom test. It tests whether there is any completion of T could reject all negative examples. We do so by replacing the hole with an empty set because the resulting regex is the least permissive completion of this template. And in this case, the bottom test succeeds. So in summary, if any of these three tests we just introduced fails, we can reject the template. Furthermore, if either of top or bottom test fails, we can reject all the expansions from T. And now we are ready to describe how we're going to solving templates using SMT solvers. Intuitively, for this example, we will generate two constraints. The first constraint saying that the initial substring phi1 that appears in the positive example should be accepted by hole 1 and hole 2 correspondingly. And similarly, the initial substring 1.5 in the negative example should be rejected. And we will generate such constraints using automata-based SMT encoding and regex-based SMT encoding. For automaton-based SMT encoding, we first need to generate a template automata from a template. Here we show the construction. For a character class hole, we will generate a transition from Q1 to Q2. And this transition could only be taken if the current character we are reading is accepted by hole 1. And for quantifier holes, the construction is similar to a repetition struct in a normal NFA. The difference here is we will introduce a counter K1 that every time we enter this sub-automata by taking Q0 to Q1, we increment the value of K1 by 1. And when we exit by taking Q0 to Q3, this transition could be taken only if the value of K1 is within hole 2 and hole 3. And upon exit, we reset the value of K1. And the rest just follows the classic construction. So given this template automata, we will showcase how to generate constraints by running an example. So upon reading the first character phi, we will invoke the transitions that is highlighted in red. So the value of K1 increments by 1, and we also generate a constraint by hole 1, for hole 1 saying that phi must be accepted by hole 1. And upon reading the second character, we take the same transitions. So the value of K2 increments to 2, and we have another constraint for hole 1. Upon reading the third character, we exit the sub-automata by taking Q0 to Q3. And when we exit, the value of K1 is 2. So we will have constraints saying the value of hole 2 is no more than 2, and the hole 3 is no less than 2. And the rest of the transitions will not change the constraints we generated. And upon reach the final state, we have all the constraints for this string to be accepted by this template automata. And this is noted as posi R1. It means S is accepted by taking path R1. Well, in general, a string could be accepted by taking many different passes like R2 and R3. So phi S denotes if S is accepted by any of these paths, then S is accepted. And for the whole repair problem, there are many positive and negative examples. And the capital phi is the final constraint we generated. It reads at every positive example, P1, P2, and so on is accepted, and each negative example is rejected. So we just finished the automata-based SMT encoding. Then we briefly talk about the regex-based SMT encoding. So given a template and an example, we will use a notation V, hole 1, hole 2, AB, to denote that AB is accepted by this template. And since the top-level construction is a concatenation, so we need, for string AB, we need to find a partition such that the first part is accepted by the first hole, hole 1, and the second part is accepted by second hole. And since there are 3 different ways of partitioning AB, so the formula is a disjunction over 3 subformulas. And the first subformula is hole 1 will accept the substring epsilon, and hole 2 will accept AB. And we could easily find the first subformula and the third subformula evaluates to false because a hole could only accept a single character instead of string AB. So the constraint is equivalent to the second subformula and eventually boils down to A is accepted by hole 1 and B is accepted by hole 2. Now we finished both SMT encodings, and still we could have multiple solutions. In this case, both solutions are correct and they have the same distance to the input. But the first one is more preferable because it could match any letters instead of some random characters. And in general, constructs like letters, numbers, and etc. is frequently used in regular expressions, so we will prefer such constructs. We will do so by introducing an objective, and this objective will increment every time we complete a hole with a lowercase letter, a capital letters, and so on. And we will maximize this objective under the capital phi. And the capital phi guarantees the correctness on these examples. And the maximization objective will bias our solutions towards using these constructs. So evaluation. We have 3 sets of benchmarks. The first set of benchmarks comes from Automata Tutor, which is a website collecting student assignments for automata theory classes. And the average size of regex is 14. And the second is from regexlib website. And it collects regular expressions from developers with average size 59. And the third set of benchmarks comes from a previous work. And the interesting point about this set of benchmarks is for each benchmark, it comes with a test set. And we can evaluate the accuracy or quality of repair by running against this test set. We also compare our tool rfixer with 2 state-of-the-art tools, regex generator++, which use genetic programming, and Rebler, which use matching techniques and adding unmatched strings to generalize a given regex. We evaluate rfixer by asking 3 questions. Could rfixer repair expressions from examples, and how does it compare to state-of-the-art tools? Could rfixer produce high-quality repairs, and which of the 2 SMT encodings is more preferable? So for the Automata Tutor benchmarks, rfixer repairs about 75% of them in less than 10 seconds. And for regex live benchmarks, our fixer repairs 23 out of 25 in 7.3 seconds, where regex generator only repaired 3 in more than 3 minutes. And for the last benchmark, it looks like the regular tool could repair all of them, but since it is a heuristic-based approach, it computes the repair at arbitrary distance. And we will show RFixer produce solutions with much better generalizability. And here is a concrete example. The expression intends to match a software name, and the solution produced by RFixer composed of 3 parts. The first part matches a publisher name, and the second part matches a product name, and the third part matches the version number. However, the regular just produces an expression that is very hard to interpret, and apparently it overfits to the existing examples. Here is a diagram showing for every benchmark that regular tool has a F1 score less than 0.8 among the test set. RFixer significantly improves the F1 score. And in general, RFixer improves the F1 score on the test set by an average of more than 100%. And here is a comparison of running time for 2 SMT encodings. RFixer A, which denotes the automata-based SMT encoding, and RFixer R denotes the regular expression-based SMT encoding. As we can see, there are many cases where RFixer A finds a solution where the other times out, and vice versa. But in general, RFixer A could terminate much faster than the other technique. And for the other 2 sets of benchmarks, the similar trend is shown here. So in conclusion, RFixer could effectively produce high-quality repair by leveraging efficient template pruning techniques and using 2 complementary SMT encodings and generalizing solution with max SMT objectives. Thanks for listening, and I'm happy to take questions.
So is there any conceptual limitation to the kind of fix that you can do for the regular expression, or your technique is quite complete?
We support the basic constructs in regular expressions, including the repetition and union and this kind of stuff. But we haven't support non-regular operators like negative look ahead and things like that.
Thank you. I think this is really interesting. So I have one question with the example you showed with the comparison with the other tool. So you mentioned one of the benefit of your tool is that you can generate regular expression that's more, I think the next slide. Yeah, sure. So your solution is more interpretable in that you can easily group things in these 3 categories. I wonder if that's an artifact of your metric of distance, or is it something that you specifically aim for to increase the readability of your regular expression?
I think that comes from 2 different aspects. The first is we impose the minimal distance repair, so it will keep the structure of the input expression. And another reason is we have the max SMT technique to use the common construct like lowercase letter and so on, so it will looks more reasonable.
Thank you.
Thanks. This construct with this template automata seems very, I guess I'm trying to understand how specific is it to this particular problem, or how generic it might be.
I think for the 2 SMT encodings, the automata-based SMT encoding is probably more suitable for this problem. But the regular expression-based SMT encoding is more generalized because it essentially models the semantics of regular expression. If one can model the semantic for some other language using the same idea, it might be extensible.
All right. Thanks. All right. Perfect time to switch. So let's thank the speaker again.